I'm going to start with questions from homework. I think at this point we've assigned up through, what, 42 or something? Yeah, 41, 42, something like that. You guys got anything for homeworks? Yeah, Joey.
Do number 31?
31, sure thing. All right, so here it asks us to find the exact value without using a calculator. The only way you can do that is if those angles are 30, 60, or 45 degrees. So I'm going to take sine of pi over 6. Look, what is pi over 6? Well, what if we just convert that to degrees? And 180 divided by 6 is 30. So that's the same as sine 30. And then we draw our 30, 60, 90 triangle. And boom goes the dynamite, right?
So does like the sign, it doesn't even matter? Or does it?
Yeah, the sign matters because now we're going to do opposite over hypotenuse, which reduces down to 1/2.
Could you number 36?
36, is that in the same section? It's a new thing, right? Yeah. So that's just doing it with the calculator. So 36 has cotangent. And now there's no cotangent button on my calculator to type in. But I remember that cotangent is the same thing as the reciprocal of tangent. So what I'm going to type into my calculator is that, and that ought to do her. Again, before I do a sine, cosine, or tangent on my calculator, I want to check my mode. I am in degree mode. I change my mode around all the time because I teach all these different classes, and AP Calculus, everything is really like radians all day, all the time. So I'm switching back and forth all the time. I got to be careful. But when I do that, I get 4.745. That's all she wrote.
So number 37, I did the same exact thing, and I got the wrong answer.
Is there a degree symbol next to the 0.34? What mode should your calculator be in?
Oh, degree.
Radians. Yeah, so that's probably why you have the wrong answers, because you didn't switch to calculator mode. Would be my guess right away if you're like, oh, I did that and I didn't get the right answer. My guess is it's a mode issue. So got to be careful about that. Yeah, sure. Okay. So this is a story problem. It says starts by saying two concentric circles. Do we know what concentric circles means? Nope. So that's the trick, right? If we can't draw the picture appropriately, how we can do the problem. So concentric means that you just have like one circle inside the other where they share a common radius, or I'm sorry, common center. Cool with that? Okay. So I'll draw here like some little sector. So it says the radius of the smaller circle, I'll call that R1, and this will be R2, the radius of the bigger circle, is 4.31, and then this is S1 and S2, the arcs. The radius there is, for the bigger circles, 5.2. And then it wants us to know what S2 is, right? So the big observation is that the theta is going to be the same in both sectors, right? the sector for the little circle is going to have the same theta as the sector for the big circle. So I have enough information in the little circle to solve for that theta. I'm going to use the radian version of our formula, just because it's an easier formula to deal with. So that's the value for theta is 5.22 divided by 4.3. And I could get a decimal out of that, but I don't really care because that's not my final answer. I'm just going to leave it as that goofy looking fraction for a minute. So in the big circle, we're looking to find the arc length. And now we have the angle measure for the central angle, and we were given the radius. So again, I'm just going to plug that into the formula, and that's all she wrote. Just calculator time from here. So about 6.29 inches. Does that feel okay, Joey? So again, if you didn't know how to draw the picture, like kind of hopeless, right? Got to have that picture to be able to like, again, the key relationship was observing that the theta is the same in each sector, right? Whether it's the big circle or the little circle. So once we found theta in the little circle, we could use that same number in the big circle. And then it was pretty easy. Cool? On to the new stuff. All right. Today, we're going to be doing sections 2, 3, and 2, 4. Remember that the goal for this chapter was we had this definition for sine, cosine, and tangent that only worked on angles that were acute, that is angles between 0 degrees and 90 degrees. Because our definition for sine, cosine, and tangent was like tied to being inside of a right triangle, right? What we're going to be doing here today is we're going to be extending that definition so that we can do sine, cosine, and tangent not on any angle measure, but on any real number. So I can do, after today, we'll be able to do sine of negative 13, or sine of 15,000, or sine of whatever number you want. Like we're going to have a definition that will now allow us to do sine of any number. It's not necessarily tied to a triangle after today. Before we can do that, though, we need to do a little bit of still building. So in geometry class, the biggest angles you could represent was what? Biggest angle you could do in geometry? You could draw. Biggest angle you can draw.
360.
What's a 360 degree angle look like? How do I draw that with like, something like this? 180, right? Because that's just a straight line, right? That was the biggest angle you could represent in geometry. What we're going to do today is we're going to create a system for drawing angles that allow us to write angles of any size, either positive or negative. Yeah, what is right? That seems weird. It's a simple enough idea, though. So what we're going to do is we're going to take the XY axis and we're going to say, okay, well, the vertex of every angle that I'm going to draw is going to be at the center or at the origin of the XY axis. And one arm of my angle is always going to lie on the positive x-axis. We call this the initial side, the side that's on the x-axis. And angles that are formatted this way, where the vertex of the angle is at the origin and the one arm of our angle lies on the positive x-axis, we call these things standard position angles. So let's say we have an angle that we cannot draw in geometry class. Let's say we have like 210 degrees. Everybody okay with that? So we need to draw the other arm of our angle now so that we can represent a 210 degree angle. So what I do is I think about, okay, I'm going to think about the other arm of my angle starting at the initial side, and it's going to rotate counterclockwise until I get to 210 degrees of rotation. So how far is a quadrant? How many degrees are there in a quadrant? 90. So I'm like 90, 90, and then like 30 more would get me to 210. So now we've shown a way to draw angles bigger than 180 degrees, right? What if it's bigger than 360? Like, let's say we have a 405 degree angle. What's that going to look like? Well, we start the same way, right? The vertex is at the origin. The initial side is on the positive x-axis. And we're going to rotate counterclockwise. So what just did it do? 90, 180, 270, 360. Nope. OneNote just thinks I want to draw these shapes, and it just really ruins my world. So I just did 45 more, and what do you notice I did? It's like a full rotation, and then just kept going, right? So at this point, you should be convinced now that we can draw angles as big as we want, correct? No matter how big you want, we're just going to we'll spin around as many times as we need to, and then we end where we end, right? Everybody feel okay doing this? All right. What about negative angles? Well, I'm going to start the same way. Vertex at the origin. Initial side, or one arm of my angle, lying on the positive x-axis. But this time, how do you think I'm going to do a negative? Spin the other way, exactly right. Instead of spinning counterclockwise, we have another direction we can spin. We'll spin clockwise. So if I do that, I have negative 90, negative 180, negative 270, and then negative 315 would be right there. Is everybody feeling okay here? Okay. So this skill of being able to draw a standard position angle is a critical skill going forward. You absolutely need to be able to draw these angles effectively. You need to be able to make sure that the terminal side is in the correct quadrant. You need to be able to tell what the angles here and here would be. But again, not hard. All we're doing is basically adding and subtracting things, right? To do that. Everybody's cool? Okay. So on this last one, we did 315. We had like negative 90, negative 90, negative 90, and then a negative 45 here. What's this other angle have to be? What's that other part have to be right in there? Also negative 45. Why is that? Every quadrant is 90 degrees, right? So if I did 45 on one side, there has to be 45 on the other. Is that cool? Okay. So again, pretty simple, pretty straightforward, not too difficult. I want to point out something here about our negative 405 and our negative 315. What do you notice about the terminal side of those two angles? So the blue one and the green one, what do you notice about the terminal side, the side that rotated? For each of those, what do you notice about it?
They ended up landing on the same line at different angles.
Yeah, the terminal side is in the exact same location, even though those are two different angles. That seems like a special thing. Let's give that a name. So we'll call those situations where the terminal side for two different angles is in the same location, coterminal angles. So the definition there, drop that in. So for example, we saw that (405) and negative 315 are coterminal. I'm going to draw two separate pictures here of these just to kind of illustrate that again. When you guys are drawing these, do I need to see the little spiral thing that I'm doing here?
Yeah. Yes.
Absolutely, yes. That's part of the drawing. So this one is the 405. That's the negative 315. Just to kind of illustrate to you like why they are, or that they are coterminal again. So if I want, how many angles do you think are coterminal to a given angle? Let's ask that question. So maybe more specific. How many angles are coterminal to theta equals 45 degrees? What do you guys think? Anybody got a number here? It's got to be at least, what?
Infinite.
You're correct. Infinitely many. Why?
Because you can just keep going up or keep going down.
You can keep spinning around one time and get there, two times and get there, three times and get there. Or you could go the other opposite direction. You could spin backwards, one time around or two times and just keep going, right? Does that feel okay to everybody? So how do we represent that? Spelling so hard. How do I represent that symbolically? So this is the way we do it. One full rotation is 360, right? So we say that all of our coterminal angles are just 45, and then we've added or subtracted some multiple of 360.
What's the K?
So the k is just like a parameter. It's like a variable, because we're saying that k has to be an integer, like a positive or negative whole number. So if k is -7, means we spun clockwise 7 times and we land back at 45. If k is 15, means we go counterclockwise 15 times and land at 45. Cool? Let's do an example here to kind of continue playing with this idea of coterminal. So let's say we want to find two angles coterminal with 47. Take a moment, try to do that. We'll take some requests or some answers in a second, but take a minute. See if you can find two angles coterminal to 47. If you need your calculator, pull it out. No biggie. All right, who's got one? Billy. 407 is one, sure. Who's got another one?
313.
What?
313. -313.
There you go. -313, that would work too. Did anybody have another one? Could you have done 767? For sure, right? How am I doing this? I'm just adding or subtracting 360 from 47. That's it. 407 is just 47 plus 360. -313 is just 47 minus 360. 767 is 47 plus 360 plus 360. And you could do this as many times as you want. Just keep adding or subtracting, keep getting another coterminal angle again and again and again and again. I don't know why you do not these ones that are relatively quick to get, but if you wanted to add 360 11 times, that's a coterminal angle. So for part B, let's see, two angles coterminal to pi over 3. So I'm just going to add 360 to pi over 3, right? No. Why not? Yeah, I need it to be in the same unit, right? So either I would want to convert pi over 3 to degrees or convert 360 to radians. Now the convention would be, since our angle is given to us in radians, our answer should be in radians. So I'm going to convert the 360 to radians. So what do I need to multiply 360 by to get an answer in radians? Do you remember that conversion factor? Pi over 180 is correct. That's one that you'll definitely want to memorize because it comes up over and over and over again. Or at minimal, put it on your note card. But I mean, like, really memorize that. You're going to use it so many times. So it's 2 pi. So I'm going to just update my thinking about coterminals to be I add or subtract 360 or 2 pi, which is the same as 360, right? To add pi over 3 and 2 pi, what do I need to do? Make a common denominator. Yes. What would the common denominator be between pi over 3 and 2 pi? 3. So I'm going to multiply 2 pi by 3 over 3. So that's going to be pi over 3 plus 6 pi over 3. So when I add those fractions together, the common denominator is obviously 3. What's 1 pi plus 6 pi? 7 pi. Everybody's cool with that? Now to get my next answer, all I would do now is I'm just going to add 2 pi again, but I already know what the common denominator is. I've already made it once. I'm just going to add 6 pi again. There's 13 pi over 3. There's another answer. And I could just keep going, adding 6 pi over 3 to my previous answer and get a new coterminal angle every time. Reminder again, if you try to do this on your calculator, it's not going to be able to give you a fraction. If I try to do pi over 3 plus 2 pi, and I tell my calculator, give it to me as a fraction, it doesn't do it. Why? The pi's in there. That's an irrational number. It won't be able to do that. But if I just leave off the pi's, and I just write 1/3 plus 2, math frac, it can do that, and I can just add the pi back in myself at the end. So if you're scared of fractions and your ability to consistently and correctly add fractions, your calculator can handle this for you. You just have to remember to leave the pi off and then put it back on when you're done. But the calculator can still do that for you. You just have to ask it nicely. So far, so good?
Yeah.
Okay. All right. So now we have all the tools that we need to move on to sine, cosine, and tangent, etc. Now that we have this new way to represent an angle, this angle of rotation or this standard position angle, now we have all the tools we need to extend our definition of sine, cosine, and tangent. So let's say that we have just some standard position angle. I want to use the same. You can call it alpha there. That little fish is the Greek letter alpha. Remember, we had mentioned that oftentimes in trigonometry we name variables that represent angles with our Greek letters and variables that represent side lengths with our Roman letters. Roman letters are just like A, B, C, D, like our normal alphabet. Okay, so here's what we're going to do. I'm going to make that a little bit longer, I think. I'm going to pick some point P on that terminal side. Anywhere on the terminal side except for the origin is fine. Because I know that from geometry, 2 points describe a line, right? That terminal side, 1 point is the origin. 1 point is this point P that I'm going to pick off of it. Everybody's okay with that? But that's why P can't be the origin, is because I need 2 points to describe that terminal side. One is the origin, the other is just this point P. So I'm going to call this P, I'm just going to give it the generic coordinates x, y. Okay, so if I wanted to plot the point xy, I would go over x and then up y. Everybody's okay with that? Look at what I've kind of made. Looks like that right triangle that we had before, right? How can I represent that side there? That distance from P to the origin. It's the hypotenuse of the right triangle, so I could do the Pythagorean theorem on that, right? So I could call this then the square root of x squared plus y squared. But woo, that's a mouthful. We're just going to call that r. So now, if I wanted to write sine alpha, I know from our previous definition that was opposite over hypotenuse. But in our new figure, that's going to be y over r. Nobody sees how amazing what we've just done is. Okay, so what we've just done is we've translated our definition of sine from being stuck inside of a right triangle where it's opposite over hypotenuse. Now sine is defined as the y-coordinate from some point on the terminal side of our standard position angle divided by the distance of that point to the origin. We no longer require a triangle to do this, right? A point on the terminal side is enough information. That's nice. That's really cool. Because I know that I can't draw a triangle that has, 115 or 107 or 198 degrees in it or something. But I sure as heck can draw a standard position angle like that. So if I do the same translation that we just did, we end up with a new definition for sine, cosine, tangent, cosecant, secant, cotangent. Are those things you should memorize? Yes, or at least put them on your note card, but you're going to use this enough times that this will be memorized, because all it is SOHCAHTOA, except for y is opposite, x is adjacent, and r is hypotenuse, right? Still just SOHCAHTOA. And I can remember that, y is opposite, x is adjacent, and r is hypotenuse. And now I have all these ones memorized also, right? So let's do an example on how we're going to use these new definitions for sine, cosine, tangent, etc. So our example says that the point -3, 4 lies on the terminal side of angle theta. Find the values of all 6 trigonometric ratios for theta. Okay? Well, let's start by drawing our picture. So 3, 4 is up there. So our initial side, our terminal side, that's our angle theta. Everybody feel so far so good? So in our new definition, I know x is -3. I know y is 4. And I know r is the square root of x squared plus y squared. Do me a favor, take out your calculator real quick and do the square root of x squared plus y squared and tell me what you get when we do this. Okay, good. You did it in your. There's a reason I'm asking you to do it on the calculator, though, because. Okay. Who got 2.65-ish? Who got 5? Okay, 2 people know how to use their calculator. A couple people don't know how to use your calculator. Which one of those numbers is right? 5 is the correct answer. The mistake you made when you got the 2.65 is you wrote -3 squared in your calculator like this. The calculator is going to strictly follow the order of operations. It's going to square the 3 and then make it negative, giving us -9. That's not what we meant, though. What we meant to type in was -3, make it negative first, and then square it to get +9. This is a super duper common mistake that I see students make really at all levels using their calculator, that we have to be careful if you're squaring a negative number to put that number in parentheses before you square it. Everybody okay? You get why I asked you to type that in your calculator now? Super easy to make the mistake. I wanted to address it while we had a moment. So R is 5. That was the point of that, though. Okay. So sine theta is y over r. So that's going to be 4 over 5. If I have sine theta, I can do cosecant basically for free because I know that they are reciprocals. So cosecant is 5 over 4. I knew what you meant. Oh, okay. Well, he did too. I know that cosine of theta is x over r. So that's going to be -3 over 5. So secant, I remember, is the, so I would write, yeah, and again, remember for like -3 over 5 is same as 3 over -5 or just -3/5, right? From our basic algebra stuff, that the negative sign doesn't really matter where it's at. Okay? And then tangent is y over x. So we have 4 over -3. So cotangent should be, fire those numbers off at me. What? There you go. I figured you're just saying it wrong. Okay. This okay though? Is it really any different than what we've been doing? No, it's a slightly different formula, but it's like the same ideas, right? All right, let's do another example. So here it says find cosine 150, and let's make the assumption we're going to do this without our calculator. So I would start by drawing the picture of our standard position angle. So 150 would be like over here, right? So that was like 90, that would be like 60. So this part would be like 30. I'm going to pick some point on my terminal side. And then I'm going to make my triangle here. What is that triangle? What kind of triangle do I have? 30, 60, 90. Oh, those have fixed side lengths, don't they? So I remember the short side. I'm going to use A instead of X. I think when I wrote it last time it's X, but we have a coordinate X. So I didn't want to get like, abuse that variable name to be like two different things. So I'm just going to use the letter A there. So what is my value for X going to be? Remember, to plot the point P, we went X over, right? And we did Y up. So what is my quantity for X going to be? I went over A cube root 3, right? Is everybody okay with that? Shouldn't be, because there's a little problem. What quadrant is this point in? The second quadrant. What should the sign on our X coordinate be in the second quadrant? Needs to be negative. Yeah, so I'm going to make that negative. So I have, again, if we forget, for any point in the first quadrant, both X and Y are positive. In the second quadrant, X is negative, but Y is positive. In the third quadrant, they're both negative. And in the fourth quadrant, the X is positive, but Y is negative. Okay. What's my value for Y? A. And what's my value for R? 2A. So if I want to do cosine of 150, then I know that's X over R. So it is negative A root 3 over 2A. And the A's reduce out, and I'm left with negative root 3 over 2. Doing okay? Then, again, a super common mistake. The most common mistake on a problem like this is forgetting the negative sign. You have to remember, like, okay, what quadrant am I in, though? Should this X be positive or negative? Have to remember to think about that. So, one more update now. We've made a procedure, right? We've changed this definition so that no longer are we locked into sine, cosine, and tangent working on acute angles and right triangles. We can now do sine, cosine, tangent, etc. for any angle. We just need to draw these standard position angles and choose a point on their terminal side. Let's standardize this process one more step. We're going to standardize the way we choose the point. Okay? So that's a place that we have choice, right? Each time we've just picked a point P arbitrarily. Now we're going to standardize the way we pick it, and we're going to pick it specifically to have a certain property. We're going to choose P from now on so that the distance from P to the origin is always 1. Or in other words, that R will always be 1. Okay with that idea? So if I do that, what do my definitions for sine, cosine, and tangent, etc. turn into? Well, sine was y over r, but since r is 1, sine is now just y. Cosine was x over r, but since r is 1, cosine's just x. Tangent and cotangent didn't have r's involved, so they stay the same. Cosecant was r over y. If r is 1, it just turns into 1 over y. And then secant was r over x. Since r is 1, and that just turns into 1 over x. Everybody's so far so good? Okay. Now that we've done this, what we're going to do is we're going to collect all these angles that we can use, or that we can find the exact values for. So all the angles that were multiples of 30, 60, 90, or 30, 45, and 60, I can find the exact values of. And I'm going to find the exact values of these angles and record them on this document here. This is called the unit circle. So 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 315, 330, and then 360 gets us back to 0. Everybody's okay? Now I'm going to record the coordinates at the point P when that distance from P to the origin is 1. So some of these points are really easy to get because it's just, well, the radius is the x or the y. So that's easy, right? And now let's do, say, the 30 degree. So if I draw my 30, 60, 90 triangle, A has to be, in this case, 1/2 in order to make R equal to 1, right? So this side becomes 1/2, and this side becomes √3/2. This is my x side. This is my y side. So I have √3/2 as my x and 1/2 as my y. All of the angles that form a 30-degree angle with the x-axis are going to have those same x and y coordinates. Just the sign might be different depending on the quadrant that that point lies in. So example, in quadrant 2, the x needs to be negative, but the y needs to be positive. In quadrant 3, they both need to be negative. In quadrant 4, the x is positive, but the y is negative. And I can continue doing this over and over again. I'm not going to spend the time to do it all right now. Instead, what I'm going to do is I'm just going to drop in the finished version here. And I'll put this in your OneNote, the finished version here, so that you can see it. So far, so good? Okay. Let's do an example on how to use this thing now. And this is the last thing for today. Oh my goodness. Okay. It says find sine of 120. So I know that I go and I find 120 degrees on my unit circle. That's right there. And I know sine is y The y-coordinate is root 3 over 2. And I'm done. Ooh! Let's do the next one. Tangent 5 pi over 4. Well, I notice that 5 pi over 4 is one of my unit circle angles. It's right there. I know tangent is y over x. What do I get when I take negative 2 root 2 and divide it by negative 2 root 2? One, close. Oh yeah, 1, not close. Exactly right. Sorry. Absolutely. Is that okay? Because I just took one number and divided by itself. Like a divided by a is just going to be 1. Doesn't matter what a is, how funky it looks. The last one, though, 390. Let's go look for that on our unit circle. Let's see, 30, 45, 60, 90, 120, 135, 180, 210, 225, 240, 270, 300, 315, 330. I don't see 390 on here. What am I going to do? I'm just going to find the thing that's coterminal to that by adding or subtracting 360 until I get a number that's on my unit circle. So I'm not doing 390, I'm doing 30 degrees. Okay, there we go. And I remember cosecant is 1 over y. So I have 1 over 1/2. Which, how does that simplify down to? Right? 1 over 1/2 is the reciprocal of 1/2. Just 2. And we're done. Unit circle. Beautiful, beautiful thing. Do we need to learn how to use this effectively? Yes. Will it be given to you on every test we take this semester? Yes. So you don't have to memorize it. You don't have to put it on your note card. I'll give it to you on every test. But you do need to be able to use it. Okay? That feels like a good place to stop. Here's the unfortunate part, is at this point, you guys should be able to do the rest of the problem set. When is this due, though? Next Sunday, not this Sunday. What is due this Sunday? Yeah, so you have 1 through 42 would be due this Sunday. And the delta math, if you haven't done that already, I think I was looking this morning, seemed like the majority of us had kind of done that already, but if you haven't, grind through those delta math problems, get that done. What else might you be expecting next week? Homework quiz, because we didn't do it today. Probably. You should be looking at 2-1 and 2-2 for the homework quiz. Focus there. No. Sure, I hope so.